We present momentum-conserving graph neural networks, a new approach for dynamic simulation of deformable objects. Graph neural networks have recently demonstrated impressive capabilities in modeling deformable materials. However, despite their visual fidelity, existing GNN-based simulators struggle to produce realistic temporal evolutions of key physical quantities. As shown in this example, they can introduce spurious changes in linear and angular momentum, leading to non-physical motion. To address this issue, we introduce a new graph network architecture that enables physically correct momentum evolution by design. Whereas existing GNN architectures predict per-vertex accelerations that can change momentum arbitrarily, our approach predicts per-edge impulses that preserve momentum by construction. Please refer to the paper for a detailed description of our method. We begin our evaluation with cloth simulation. We compare our model against mesh graph nets. We use the publicly available code and train on the cloth sphere dataset. As can be seen in this example, mesh graph nets performs reasonably well on the original test case. Our model produces qualitatively similar results, but exhibits more dynamic motion thanks to its inherent momentum conservation properties. The picture changes drastically when releasing the cloth from its pin configuration. Mesh graph nets now produces spurious momentum changes during free fall, causing the cloth to drift and accelerate in a direction inconsistent with gravity. In contrast, our method produces the physically correct behavior. To confirm this observation, we retrained mesh graph nets on the same dataset as our model using a self-supervised approach. The drifting effect persists. The cloth fails to properly fall and settle onto the torus. Correcting spurious momentum changes using velocity projection can eliminate drift, but unphysical folding artifacts remain. Our method again produces physically correct freefall motion and realistic folding after contact. Additionally, our method readily generalizes to more complex perforated star shapes. We next evaluate our method in the context of elastic solids. In this example, a beach ball is thrown toward a basketball hoop. Using conventional implicit Euler integration, the ball follows a natural trajectory and successfully scores. When using mesh graph nets, the ball exhibits erratic motion with spurious injections of momentum. Adding velocity projection again helps guide the ball toward the hoop, but it misses the basket and displays unphysical rotational behavior. Our method, by contrast, produces accurate evolution of linear and angular momentum and successfully completes the throw. We further test our model by simulating a tennis ball dropped onto a table. As can be seen, our approach closely tracks the behavior of implicit Euler, producing natural bouncing motion. Our method also captures the right damping behavior from the reference simulation, leading to gradual decay and rebound amplitude. In contrast, mesh graph nets completely fails to predict reasonable motion for the ball. When combined with velocity projection, the trajectory becomes more realistic, but the ball bounces off the table due to spurious momentum changes. Although we only train our method on simple shapes such as cuboids, it generalizes to complex unseen geometries, such as this armadillo. In this example, we start simulating from a deformed pose. Since the initial velocity is zero and there are no external forces, the total linear and angular momentum should remain zero. When using mesh graph nets, however, the armadillo quickly drifts off screen, thus violating momentum conservation. In contrast, our method produces realistic, dynamic motion while satisfying the global momentum constraints. When we augment mesh graph nets with velocity projection, the drift is reduced but deformation artifacts appear. To further analyze our method, we perform an ablation study. We simulate the armadillo using our architecture, but replace our momentum-consistent velocity with the finite difference velocity used by mesh graph nets. As expected, this substitution introduces gradual changes in orientation. confirming the importance of consistency between position and velocity for momentum conservation. Thank you for your time.